Hello, this is a video presentation for the paper Almost Linear Time Parameterized Algorithm for Rank Width by a Dynamic Rank Width created 1, 2, 1, 1, 1, 3, 2, 1. Hello, I'm Marek Sokołowski, and this is a video presentation for the paper Almost Linear Time Parameterized Algorithm for Rank Width via Dynamic Rank Width created by me and Tuka Korpanen. So let's understand what the title says, and let us understand the notion of rank width of undirected graphs. So in the notion of rank width, we aim to recursively decompose the set of vertices of a graph G. So as follows, we create this kind of a rooted binary tree over the set of vertices with the set of vertices of the graph, so that the leaves of the graph of the tree are identified with the vertices of the graph. Okay, and what we want to achieve is that every cut in that tree, this kind of tree, should be somehow simple. So what does it mean to be simple? So whenever I take any cut in the tree, it splits the set of vertices into two parts here, 1, 2, 3, 4, and 5, 6, 7, 8, 9. And I want the connection, like the graph showing the connections between the sides of the cut, to be as simple as possible. And for the case of rank width, what we care about is the binary rank of the adjacency matrix of the cut. So here we can observe that each of the vertices 1, 2, 3, 4 is adjacent to each of the vertices 5, 6, 7, 8, but non-adjacent to vertex 9. So this adjacency matrix is very simple, with a lot of ones, like with the constant column ones and constant column zeros. So its binary rank is 1. Let's consider one more cut between the vertices 1 through 6 and 7 through 9. And its adjacency matrix looks as follows. And it can be observed that this adjacency matrix has binary rank 2. So if we interpret that matrix as a 0-1 matrix in the binary field, its rank in the binary field is 2. Okay, and now the width of a cut between the set of vertices x and complement x is the binary rank of the adjacency matrix of that graph, of that cut. Then naturally the width of the rank decomposition of a graph is the maximum width of any possible cut given by this tree decomposition. With those two cuts we already observed being some 2 examples of such cuts. And the rank width of a graph is the minimum width of a rank decomposition of the graph. And it can be observed that this rank decomposition has actually rank 2, and the rank width of the graph is 2. Okay, so let's first tie rank width to a couple of different notions that are more suited to sparse graphs instead of arbitrary graphs. So there could be a case there is a case to be made that one of such sparse variants could be branch width, where we define the width of the cut slightly differently, namely as the number of edges between the sides of the cut. And then we reuse the definition of rank width, namely the width of a branch decomposition of a graph is the maximum width of any cut given by the tree, by the decomposition. And the branch width of a graph is the minimum possible width of any branch decomposition of the graph. And if you know a thing or two about graph parameters, you probably know that branch width is linearly tied to tree width. So whenever tree width is bounded, branch width is also bounded of a graph or a class of graphs, and vice versa. So somehow we have an argument to be made that rank width is a kind of a dense graph variant of tree width. There are actually countless different reasons why rank width is actually a dense graph variant of tree width, but this is one of such reasons. And it turns out that there's a lot of different graph parameters that are functionally equivalent with rank width. So rankwidth was initially introduced. We have this rankwidth, which is initially introduced by Owen Seymour in 2006. But we have this original definition of click width by Purcell, Engelfried, and Rosenberg back from 1993. And we actually have a notion of NLC width that's quite similar to click width, described by 1K in 1994. And we have a few notions that are similarly defined as rank width, but with this binary rank of the adjacency matrix replaced by slightly different notions. So for instance, we have Boolean width, we have F rank width, where we replace the binary field with an arbitrary field. In particular, we could use the field of rationals instead of the binary field. And now, if you don't know much about rank width, you would be entitled to have a question, why should I even care about this thing called rank width? And it turns out there is a good reason to actually care about rank width, and it's a logic reason. So there's this theorem of Kursel-Makowski and Rotix that says that whenever I have a graph property or a graph optimization problem that's expressible in the variant of monadic second-order logic called CMSO1. So it's like monadic second-order logic with counting predicates and the predicates of the form there exists of the set of vertices, or for all sets of vertices, something happens. And such graph properties or optimization problems can be verified or solved optimally in graphs of rank width at most k in time linear with respect to the graph, as long as we are given a rank decomposition of that graph of width at most k. Okay, so for instance, it turns out that the problem of maximum independent set is expressible in CMSO1 logic, so it can be solved in linear time on graphs of bounded rank width, and can be solved optimally. Similarly, the problem of minimum dominating set of a graph can be solved optimally in linear time, given the rank decomposition of the graph. And for instance, the property of three-colorability of the graph can be also expressed in the CMSO1 logic, so it can be tested in graphs of bounded rank width in linear time. And for instance, as soon as we have this graph property, it can be turned into a graph optimization problem of finding the maximum set of vertices that induces a three-colorable graph. Okay, so we have this well-known Kursell's theorem that says that for this sparse counterpart of rank width called tree width, we can devise efficient algorithms for a slightly larger variant of logic called CMSO2, where we additionally permit quantifying over the sets of edges instead of just sets of vertices. And to summarize the theorem above, for bounded rank width and or click width, we can devise efficient algorithms for problems expressible in CMSO1 logic. And it turns out we have, in some sense, converse implications. Like, without getting into details and very technical stuff, I would just roughly say that bounded tree width is a kind of a boundary of tractability for problems expressible in CMSO2 logic. And similarly, bounded rank width and click width is the kind of boundary of tractability for problems expressible in CMSO1 logic. Okay, but the problem is that this Kursel-Makowski and Rotix theorem requires that a rank decomposition of the graph be given on input. And this is a pretty high ask, since usually when we solve problems, we are just given a graph and we want to solve a computational problem on the graph. So the issue is that we need to compute an optimum width rank decomposition of the graph, or maybe even a near optimum width rank decomposition of the graph. Okay, so let's now walk through some of the algorithms we know for computing rank decompositions of the graphs of optimum or near optimum width. So first of all, in 2006, when Owen Seymour described the notion of rank width, they produced a 3 approximation of this parameter that works in polynomial time, something like n to the power of 9, and it actually works for a more general concept of connectivity functions. So when you replace this concept of a rank of a cat with something much more general called a connectivity function, their algorithm also works for this kind of a general case. Actually, Ohm and Seymour introduced the concept of rankwidth to approximate the value of click width that was introduced about a decade earlier. Then, a year later, the same set of authors produced an exact with rank decomposition and connectivity function decomposition algorithm, but at the cost of having an algorithm whose complexity is a polynomial whose exponent depends on k. Next, Ohm described a three approximation algorithm that works in n to the fourth time, and also a three approximation algorithm that works in cubic time at the cost of a much worse dependency on k. Also, Korsel and Ohm in 2007 produced an exact cubic time algorithm for rankwidth, but the issue is that it could only compute the value of rankwidth, and it could not recover the optimum width rank decomposition of the graph. This was later fixed by Kleinini and Ohm in 2008, who actually produced a cubic time algorithm computing the exact optimum width rank decomposition. And much later, this was generalized by Young, Kim, and Ohm in 2021, who gave a cubic time algorithm that also worked in a more general context of spaces over finite fields. So it's a specific kind of connectivity functions that describe somehow dimensions of various finite fields. And rankwidth is can be cast as a problem for optimizing spaces over finite fields. Then in 2022, there was a paper of Fiedler and Korhonen, a breakthrough paper, in my opinion, who gave a quadratic time algorithm for the problem. And eventually, we have our work, which computes exact with rank decomposition in time that is almost linear in the number of vertices of the graph. So we have n times some sub-polynomial factor in n times some factors depending on k, plus additionally, a summand that is truly linear in the number of edges of the graph. Okay, so let us state our result formally. We have an algorithm that can input an n vertex and m edge graph and a parameter k, and at time almost linear in the number of vertices of the graph times some factors dependent on k, plus something truly linear in the number of edges of the graph, either outputs a rank decomposition of the graph with at most k, or correctly deduces that the rank width of the graph exceeds k. Okay, so in the positive case, we can also do a couple of more things. First, we can also output a so-called expression, which is a kind of a decomposition for click width that proves that the click width of the graph is at most exponential in k. And it can also solve any fixed problem expressible in CMSO1 monadic second order logic. An additional time that is linear with respect to the size of the graph, with additional factors that depend on the width of the graph, or that's the rank width of the graph, and the graph problem. Okay, so the important takeaway here is that if our input graph is sufficiently dense, as in the number of edges is larger than this funny expression, n times something a subpolynomial in n, we actually get a truly linear time algorithm determining the width of a rank decomposition of this graph. So the only remaining thing is to show a linear time algorithm for the sparse case. Okay, let's now spend the remaining 10 or so minutes to give a rough idea on how almost linear time algorithm for rank width is achieved. So the main part of our proof is the so-called dynamic rank width data structure. So we have a data structure that maintains an n-vertex dynamic graph of rank width at most k that is updated by edge insertions and removals. and it can store at each point of time a rank decomposition of the graph of width at most for k and some sub-polynomial height. And the amortized update time of this data structure is also sub-polynomial in n. Also, this data structure can be amended so that it can maintain a solution to any fixed CMSO1 problem we like for that graph. Also, a quick mention that the types of updates we can permit in this data structure can be a bit larger, like we can permit kinds of dense updates in the graph, but for simplicity, we only state this basic version of the theorem here. Okay, and let's now go through 4 different things we use in the proof of this dynamic rank width data structure theorem. There are some more, but those are the ones that I believe are the most important. So first of all, we take a lot of inspiration for the dynamic tree width result of me, of Tuka, of Konrad Majewski, of Wojciech Nadara and Michał Filipczuk back in 2023, where we maintain a low height decomposition of the graph by noticing that if I do any small graph updates, such as remove or insert an edge to the graph, I will only break this width invariant where the width of some edge increases above 4k only somehow locally. So it somehow makes sense to only recompute local prefixes of this decomposition using a really clever amortized time refinement operation. This refinement operation is pretty complicated, so I will unfortunately have no time to describe how it works, but you should think that whenever I have some edges of the graph that break this width invariant, I try to fix them around by refining some small prefix of the decomposition. On the other hand, this refinement operation might cause the height of the decomposition to become too large. So we also give a height improvement operation that intrinsically works by performing a sequence of refinement operations. So we have this funny thing where refinement operations can increase the height and cause it to be too large, but the height improvement is actually implemented through refinement operations, and it can be proved to decrease the height of the decomposition below a subpolynomial threshold. Okay, and interestingly, it turns out that the combinatorics of rank width are much cleaner for rank decomposition case than in a tree decomposition case. So it maybe makes sense to restate the combinatorics of dynamic tree with data structure in terms of dynamic rank width, or graph parameters defined similarly to rank width, such as, I don't know, branch width. Okay, let's move on to the so-called the alternation lemma for rank width, which is a structural theorem for rank width that is adapted for its tree width analog given by Bojańczyk and Filipczuk in 2022. So for rank width, the alternation lemma reads as follows. Suppose I have a graph, and I have some rank decomposition of the graph of possibly non-optimum width L. Then I have an integer C that depends only on this width of the decomposition L and not the decomposition of our graph itself. And there exists an optimum width rank decomposition, say T, of that graph. I don't know what it is. I don't know how to compute it, but I know it exists somewhere in the limbo, such that for every cut of this non-optimum width decomposition, separating X from the complement of X, I can represent X as a sum of at most C different factors of the optimum rank decomposition T. And here, if you need to know, a factor is either a side of the cut of the optimum width tree decomposition, or the difference of two sides of two different cuts of the optimum width rank decomposition. And we prove it by using quite similar methods as in the proof of the original the alternation lemma for tree width given by Bojańczyk and Filipczuk. We heavily rely on the structure theorems from the cubic time algorithm of Young, Kim, and And we also add a lot of hard work and combinatorics and work on linear subspaces, linear spaces, dimension computations, whatever. There's a lot of stuff happening there. But yeah, mostly it's methods from the dimension lemma for tree width and the structure theorem for rank width by Young, Kim, and all. Okay, let's now move on to automata. So the interesting thing here for tree decomposable classes of graphs is that whenever I want to solve some problem, say CMSO1 problem, or want to do some dynamic programming on some kind of a tree decomposition on a graph, it can be usually stated as a kind of a tree automaton, where tree automaton is a notion in the from the automata theory. So for instance, for the sparse case, we can define the so-called tree decomposition automata for tree width. And Courcell's theorem says that we can use those to solve CMSO2 problems for graphs of bounded tree width. And in this case, we have click expression automata for click width that can be used to solve CMSO1 problems, as mentioned a few slides ago. But the problem with click decompositions or click expressions is that those work really well with those kind of tree automata, but those are really hard to compute or maintain without explicitly, without using different approximation algorithms, going through rank width and then doing some transformations to actually produce click decompositions. On the other hand, we have rank decompositions that we already know how to compute quite efficiently, but it's really not clear how to define automata on rank decompositions. So what we do is we actually set up some non-trivial and extensive maintenance of different annotations throughout the rank decomposition to actually produce a notion of rank decomposition automata that is used throughout the paper. Okay, finally, one of the automata we actually define and heavily rely on is the exact rank width automata. So you might know for the sparse case that Bodlander and Klotz back in 1996 produced a tree decomposition automaton that input a tree decomposition of the graph of width L and determines whether this graph has tree width most k, where k is usually smaller than L, in time exponential in k and L. But the important takeaway is that this complexity is linear in the size of the graph, or the size of the tree decomposition automaton. So we had a kind of a similar case, but not really for rank width. So Young, Kim, and proved that there exists a dynamic programming scheme that inputs a rank decomposition of the graph of width most L and determines whether this graph has rank width most k in time that is n squared instead of n. And here, this dynamic programming scheme didn't really translate too well into automata. Some parts that translate really well, but there were unfortunately some parts of it that didn't translate really well. So in our work, we actually described an automaton, a rank decomposition automaton, that inputs a rank decomposition of width most L and determines whether G has rank width most K in time linear with respect to the size of the graph. Okay. And finally, I would like to describe how dynamic rank width is very briefly used in the construction of a almost linear algorithm for rank width. So if we are okay with an almost linear time that is not linear, fully linear in the number of edges of the graph, the only thing that's necessary is to sort the edges of G in some appropriate, well-known way, add them to the dynamic rank width data structure one after another. And it turns out that whenever the rank width of the input graph is most k, then this order of insertion of edges will ensure that the data structure will always hold the decomposition of width at most 4k plus 4. So the additions of all edges can be done efficiently. And then we can use the exact rank width automaton to actually recover an optimum width decomposition of the graph. For truly linear time in the number of edges of the graph, we devise a really neat divide-and-conquer scheme where the dynamic rank width data structure is hidden under the hood. And in order to have a truly linear dependence on the number of edges, we actually use some funny hacks like storing the edges of the graph in suffix arrays. Okay, with that, I would like to thank you for your attention.